Hey, good morning, everybody. Or good afternoon. Good. All right, how are people today?
Did you shave your hair up since the last quarter?
I got a hat on. I think that's the only major change.
Different lighting.
Different lighting. Oh, different color maybe. It changes color frequently. All right.
Yeah. What's the brightest color you've done?
I went blonde for a few years. I also went orange for a while. And my head was completely shaved for a few years also. So, I've had a lot of different hairstyles.
Like to try stuff out?
Yeah, I get bored quickly, so, you know, stuff to do. This is why I could never get a tattoo, because, like, I'm too fickle.
No, the problem is you get one and you keep getting them because you're bored with the ones you already
have. Right. Yeah, I've heard that too. All right. Well, so welcome to winter quarter. If you were in 215 yesterday, you already heard me say welcome. But if not, welcome to the new quarter, and welcome to CSE222. So this is the second 200 level CS course in the sequence, following 224, which most people took in fall. And this is a data structures course. It's all about programming in C, and in particular about learning new ways to organize information in a program, to take our variables and treat them in a way that makes sense with respect to what the data is that these variables represent. And so we're going to learn lots of these data structures, things called linked lists, binary search trees, hash tables, stacks, queues, all kinds of good stuff. Data structures are sort of one of the main pillars of doing programming for a living. You'll work with a lot of data structures, and knowing how to organize your information, how to structure your data, is often one of the first things you do when you're trying to write a large program. If somebody says, you know, I want you to write a program that will let me, you know, record student information and, you know, give me averages and things like that, one of the first things you do is you figure out, you know, what kind of data do I have and what's the relationship among the different pieces of data, and that defines your data structure. So this is a pretty foundational course, and it's done strictly in C. We might talk a little C++ at the end, but it's pretty much a straight C programming course. And we don't teach programming per se. We assume at this point that you know how to program, that you understand the basic mechanics of C, but we will spend a lot of time dealing with pointers and you know, the funny ampersands and stars we put in variables and things like the malloc statement and so on. We're going to start with all of that today, actually. So those kind of more advanced mechanics of C we'll definitely spend time working on. But as far as you know, what is a C program? How do I write a main function? What are conditional statements? Right, you want to be up to speed on those, and if you're feeling rusty, definitely spend some time, you know, today doing some review, because we're going to kind of hit the ground running as far as programming. We don't do bash programming in this course, but you know, if you're working in a Unix environment, you're probably working in a bash shell, and you can continue to use bash for your own, you know, work that you're doing to organize your code and move around your file structure and so on and so forth. So so it's a very different sort of feel material-wise from 224, and it's just, you know, totally focused on programming in C. All right, and we've got 20 people in class, so we're missing about 20% of the class right now. But I'm going to go ahead and get started. And let me begin with an announcement, which is a request for a note taker. So I've been asked to read the following announcement in class. A student in this class has a documented disability that impacts his or her ability to take comprehensive lecture notes. and we're requesting that one or preferably two students in this class volunteer to share their notes. And so this would basically be, you know, as you take the course and you write your own lecture notes, probably scanning those and sending them into the Disability Support Services office, and they would share this to the students who have this note-taking accommodation. If anybody in here is willing to do that or interested in finding out more, please send me an email, okay? And I'll give you the information that you need to contact the DSS office, and they can set you up as a note taker and tell you how to get your notes and so on and so forth. And it's just as a general comment, note taking is a really, really good skill. And it's a really good discipline to practice for yourself. We're meeting for 2 hours a day, 2 days a week, right? A little over 2 hours, so like 130 minutes, I think. If you just sit there and listen to me talk for 130 minutes, that's not going to be a lot of fun. It's not going to be terribly useful to you, right? I mean, you could watch a 2-hour YouTube video and hear a lot of the same things that I'm going to say. What you really want to be doing during lecture is kind of engaging your mind and thinking about the material as we're talking about it, right? So, you know, this is about active learning. It's about thinking about what we're discussing as we're discussing it. And one way to kind of help keep yourself engaged is to take notes. Now, you don't need to write down anything that I say, because everything that I write down, everything that I say is recorded, right? And these will be posted after class. So you can go back and you can see, you know, what was that line of code that he wrote, you know, an hour into the lecture. So you don't need to take notes in order to be able to look at that information again. But the process of writing notes, of taking a concept and turning it into, you know, the mechanical motion of moving a pen, that helps code information in your mind different ways from just hearing it passively. So I strongly recommend taking notes for yourself, if nothing else. But if you're taking notes and you're willing to share those, right, then you can also help out some fellow students in this class. All right, so let me hop onto Canvas and just kind of go through some of the basic highlights of this course as it appears on Canvas. So I'll start with the syllabus and additional course policies, because those are kind of the main working parts of the course. As we're talking about this, if any questions come up, if you want further clarification on anything, or you want to make a comment, feel free to either hop in chat, or just use your microphone and say, hey. And I'm just realizing this quiz was due the 4th, and the 4th is today, so I'm going to actually change this to the 5th. This quiz is just a getting to know you quiz. It's just to make sure you can get on Canvas and take an online quiz. It's a 1-question quiz, which says, what course are you currently sitting in, right? So I'll give you a hint. The answer is CSE224. But take that just to make sure that you you know how to do quizzes on Canvas.
This isn't Scuba 101?
It's not Scuba 101, even though that's what I normally teach at this time. I'm going to do data structures instead.
What is Scuba 101?
I assume it's an intro to scuba diving course, which would be pretty cool. Actually, I think Clark teaches scuba. Yeah, it's not 101, but Clark does teach that, I believe, because I've had students who take it. And
Cool.
they teach it in a pool. Yeah, I mean, if you have to take PE anyway for the AST degree, you could take scuba.
Wait, you have to take PE?
For the AST2 degree, you need 2 credits of health, 1 credit of PE. To transfer to WSU, you don't need those. But if you want to get the actual associate's degree from Clark, then you need 3 credits of health and PE.
Gotcha.
Yeah. Yeah, someone says the dilemma I've always had with note taking is the difficulty of listening while writing. I have that issue too somewhat. This is one argument in favor of taking notes by hand instead of trying to type them, because you can develop some skills with writing notes while you're listening. But yeah, it can sometimes distract, but it can sometimes reinforce. So things to try. All right, let me talk about the syllabus, and I'm just going to go from my version of the syllabus instead of trying to blow it up in Canvas. So yeah, go ahead.
The Introductions to Algorithms, 3rd edition, there's an easy to find free PDF for that. It's the first link on Google when you
Okay.
look at the...
Cool. All right, so this is CSE222 Data Structures course. You can read the description, topics, prerequisite, all of that kind of stuff. The required text is Open Data Structures. It's a free open source PDF download, so there's a link to it here. It's a good text. I don't recommend printing it out, but I recommend downloading the PDF and having it available. It covers a lot more than we'll go through in this course, but it's a really good reference to keep on hand. Recommended text, so Introduction to Algorithms by Corman is sort of the gold standard of algorithms, and there's a lot in there. Most of what's in there we won't get to. This is more a data structures course than an algorithms course. But in other courses down the road at university and so on, you'll deal with a lot of different algorithms. That's a really good reference for looking those things up. On the other hand, nothing that we're doing is terribly new, right? The stuff that we're talking about is, at least 40 or 50 years old. So you don't need like the latest cutting edge, textbook or outline on this material. It's pretty well established stuff. The C primer, that big book from 121, is still a good reference for C, and some sort of guide to Linux. The 224 text is a good one for that too, just to help you get around the Linux environment and so on. You want access to linux.enjrcs.com. That's the server we use for this class. The only thing you need that for, though, is to make sure that your code runs on it. So you can develop, in whatever Unix environment you want. If you have your own Linux laptop, you can do your development on there. But I'm going to test your programming assignments on this Linux server. So at the very least, you want to upload your code there, run your make file, run your test cases, make sure your code works before you submit it to Canvas. Just to make sure you're not, taking advantage of some peculiarity on the system that you're working on. But if you don't have access to a Linux machine, this is a good one for you to use. So
are we just going to kind of do like we did in 224? We'll upload to a new directory on GitLab kind of thing, and that's where you'll get it from?
So I am not doing Git for 222. So
Okay.
I encourage you to continue to use Git to organize your work, to keep backup copies, and so on. But I'm not going to take submissions through Git. You're going to submit your programming assignments through Canvas. So that'll be a change in modality.
Or something?
You'll submit it as a tar file, and we'll talk about what that means. Yeah.
Okay.
And yeah, you should have your same account from 224. Now, if you were in 224 in fall, your account is still set up exactly as it was. If you were not enrolled in 224 in fall, I created an account for you if you were enrolled in this course as of the weekend. And I'll show you the how-to in Canvas that tells you what the machine is, how to log in, your username, password, and that kind of stuff. Someone said Git habits were the best takeaway from 224. Definitely good news. Git is still your friend. All right, so you can read through the course outcomes. These won't make a lot of sense until we actually get to these topics, but these are, the details of the specific things that we intend for you to learn in this course. And when you transfer to a university and they see that you've taken CSE 222, these are the things they expect you to have an understanding of. So these are the course outcomes. Topics to be covered, same thing. You can read through these now and as we go through the course, but they won't make a lot of sense until we actually get into these topics. Course policies, most of this you've seen before, and so I'm not going to read through all of this because there's 4 more pages from this point on. But let me point out a few things. So academic honesty and plagiarism. I don't want to dwell on this a lot, but basically, you know, make sure the work you're doing is your own work. Make sure the work you turn in is your own work. Don't go to online sources, Stack Overflow, Course Hero, Chegg, those kinds of places. Don't copy code from anywhere else. Don't share your code with anybody. Right? I've had cases where a student does their own work, but then they show their code to somebody who's struggling, and their friend turns that code in as if it was their own. If I get two submissions that are the same code, both get a 0. Right? And it doesn't matter if you're the one who copied or the one who innocently gave your code to a friend to help them out. Right? So err on the side of caution, and if you're in doubt, just ask me. Right? And I'll help you figure out, you know, what's a good thing to do here. If I find evidence of you know, somebody turning your work that's not their own, or you know, work being duplicated among students or online sources or something, it's an automatic 0 on that assignment. If it happens a second time, it's an F in the course. And if there's a dispute, if I look at the code and you know, this is exactly something that I find online, and the student, you know, swears to me that they wrote it themselves, and there's, you know, a deadlock there, we'll just pass it to the honor board, and they can do the investigation and dig in and try to understand what happened. So best advice, right? If you're in any doubt about what's legitimate, what's over the line, and so on, just ask me. And there's never any harm in asking, right? All right, late papers and assignments. So you have 4 slip days available this quarter, and you can use those for the programming assignments, but that's it. You can't use them for the midterm or the final exam or the online quizzes. Okay, but you can use those 4 slip days to turn in any or all of the programming assignments late as you choose. All right, we'll talk more about details of that. But unless you're using a slip day on a programming assignment, if things are not turned in by the due date, it's going to be an automatic 0. Don't miss your exams or other deadlines. That's a bad thing to do. So, and this is an entirely remote course, so we don't have to worry about you know, not being able to come into campus because of symptoms and such. All right, ADA accommodations. So make sure you read through this. But the basic punchline is, if you feel like you're at a disadvantage because of some sort of disability, and you feel like an accommodation would help you be more successful in the course, talk to me or talk to the DSS office, and we can arrange a variety of accommodations. For example, if you have test anxiety and you need extended testing time, that can be arranged. If you're taking an in-person class and you need to sit in the front because you can't see the board from the back, we can arrange to have a seat in the front reserved for you. Not a factor in this class because it's remote, but this applies to all your classes. If you need to sit in the back of the class because you want a wall behind your back, right, we can arrange to have a chair in the back of the class. Note-taking services, flexible attendance policy, and so on and so forth. So any concerns or thoughts around that, talk to me or talk to the DSS office. And there's phone numbers, there's websites, and there's emails you can use to reach them.
Isn't this the remote-only class, though?
This is a remote-only class, so the attendance issues, the you know, seat issues aren't a factor, but for other classes it could be. Let's see, is there a way to change my Linux server password? For some reason I can't log into the server. Yes, go ahead and send me an email with your username, and I'll reset your password for you. But send me an email to remind me. All right, non-discrimination policy. This cuts across every class you take at Clark. Make sure you have read through this. I've read this. I read this to my 101 class, word for word. I'm not going to read through it in this class, but make sure you've looked at this, and it should be pretty self-explanatory. Same thing with Title IX. Same thing with sexual misconduct. There's contact information in here if these issues come up. But again, you know, you can always, you know, come to my office hours, send me an email, get in touch with me, and I can take you through more of the details on this if you feel like there's a situation that we should deal with. College-wide student information. You can click through here to see this. Food, housing, and financial aid help. So we're still in a global pandemic. We're in a worsening global pandemic, actually, and there's a lot of uncertainty. There's economic uncertainty. There's uncertainty with housing. If you find yourself in a situation where you're struggling financially, you're struggling with housing or with having enough food and so on, there's help available through Clark, right? So partly through the CARES Act, and various funds from the foundation, right? There's resources available. So there's some information here you can click through to read more. But Kath Busha this is their email address. They're definitely the person to talk to, right? They're in charge of student engagement, and they can help you, find resources that are available, point you to other resources, and so on and so forth. So if you have any issues like that going on, definitely send an email to Kath at that email address. Reasonable accommodations for religion/conscience. So if you need to miss a course because of a religious holiday, something like that, you need to miss a day, things like that. That's all protected, right? So you can read more about that at this website, or get in touch with me. All right. This is a remote class, so we're not going to be coming into campus. Everything's going to be done online. Everything's going to be submitted online. So these COVID-19 mitigation efforts don't concern us for this class. But I want to make sure if you're taking any in-person classes and you haven't already looked at this, make sure you look at this. Okay? I've already heard from a handful of students about COVID symptoms, about exposure to people with COVID and not being sure what to do about it. There's a lot of information out there, and in some sense there's almost too much information. It's hard to know, where do I go to find out what to do if I wake up with a fever, right? Who do I talk to? What do I do? What don't I do? So you can find some of that through here. And we're not going to have to worry about wearing masks and cleaning workstations and so on and so forth, because we're in person. Yeah.
For the YouTube playlist that you keep your videos up to date on, are they going to be considered 222B?
Correct.
Okay.
All right, and then Code of Student Conduct is same as usual, and then the Engineering Computer Science course policies, you can click through here.
Not to jump ahead here, but
Go for it.
I was wondering if there are going to be any coding guidelines to follow, like Bash and SCANA for 224.
No. As long as you're doing your own work and writing your own code, and you're working in C, you've got a pretty good amount of flexibility. Now, if you're thinking of doing something really bizarre, ask me about it in particular. Like if you're thinking, oh, I'm going to write my stuff in assembly language and embed it with assembler directives, shoot me an email or come to my office first and let's talk about it. But within reason, right, pretty much anything goes. Does that make sense?
I'll have to try messing around with inline assembly this time.
But I don't have, specific requirements for what kind of indenting style you should use, or should you put your curly bracket on the same line as an if or on the next line, and things like that, or you can't use variables with fewer than 3 letters in their name or things like that. You'll find these kinds of guidelines at other schools, and you'll find them on the job, but I'm not going to do those kinds of things. But I want code to be well written. I want it to be indented in some kind of consistent way. I want comments throughout the code, and we'll talk about those in detail when we talk about the first programming assignment, which we'll do on Thursday. All right, so additional course policies. These are kind of the specifics for this this offering of the class. All right, so grade calculation. You're going to have 5 programming assignments, roughly 1 week each, which will cover, some of the major topics we're going through. Those are combined for 30% of your grade. There's a series of online quizzes on Canvas, which you can take anytime you want, beginning with the first quiz, which is, just the 1-question quiz that's due tomorrow. Total quizzes, 10% of your grade. Midterm is 20%, final is 30%, service learning project is 10%. So pretty straightforward grade calculation. There are no ODPs this quarter, okay? And there's no in-class quizzes, things like that. No homework other than the programming assignments.
Kind of a bummer. I like the ODPs.
I like the ODPs too, but I feel like they're getting a bit astray from the original intent, which was to sort of help people in their learning of the material. And for some reason, I feel like the way I've been doing ODPs has started moving students towards concentrating more on the ODPs than on the larger topics. And I'm finding when people get to the programming assignments or the questions on the exam, they're kind of trying to turn the ODPs into their answers, and that's not really the intent, and that's not really a ideal situation. The other thing is that when you move on to university, you're not going to have the ODPs. You're really going to need to have the skill set to say, okay, so we're learning about hash tables, and I don't really understand what the hash function is all about. You want to be able to sit down and write some code to test your understanding of it, to play around with things. That's what the ODPs are intended to do, and I think they did that in 224. But ultimately, you want to be able to figure out, sort of test code on your own and get comfortable with the idea of, what was that scanf thing that he was doing in class? Well, let me write some code and play around with that and see if I can reproduce those results and then find some new application, So we're gonna leave ODPs aside for this class and maybe bring them back in 223. We'll see. All right, you can read through the keys to success. You've heard me talk about these before, but basically, right? Come to every class. Try to come on time. Plan to stay for the whole class, and try to be active. Right? Try to participate. Answer questions when I ask them. Stay engaged. Ask questions if you don't understand something or you're unsure about something. Don't give up when you're trying to do something and it's not working. Don't just, throw away your program and start over. Work through the problems, right? Don't just try to get rid of them. Try to understand them. They are the best learning opportunity that you will encounter. When you find a bug and you cannot figure out why your program's not working, that's the gold, right? That's the thing that you really, really, really want to dig into and understand. That's worth more than all of the lectures, all of the videos you can watch, and so on and so forth. So bugs are your friend. And the rest of this you've heard me say before, right? Stay in Linux, work on the command line, use VI. These things let you concentrate on coding, right? But force you to do the things that help you write code, like indenting and knowing the syntax and so on and so forth.
I do have to ask, did you ever write a script to help you with the attendance pings?
Yeah, I did, and I debated what I was going to do with attendance this quarter. Same with slip days, and in the end, the best solution I could come up with was just not to take attendance. So we're not doing attendance this quarter. And hopefully after 224 and other courses people have taken, you've got a pretty good understanding of how important attendance is or is not for you in different classes. And if you're not coming to class and you find that that's hurting your performance, hopefully you'll adjust and you'll start coming to class. And so I'm going to leave people to figure that out themselves, and I'm not going to take attendance and record attendance. All right, getting help. Absolute best way to ask for help, to ask for clarification, to ask questions is during class. All right. it's a 130-minute class session. That's a long time to talk. It's a long time to listen, right? And, you know, if I start talking about pointers 5 minutes into the class and for the next 2 hours you have no idea what I'm talking about because you didn't catch what a pointer was, right? You're wasting your time, right? So ask questions. And guarantee, you know, if you're unsure about something, so are other people. If you say, you know, so wait, why did we put the ampersand there instead of there, right? Guarantee there's other people who are going to be like, oh, you know, thank goodness someone asked that. So ask questions, right, during the class. That's your absolute best way to get help. If that doesn't work, or if you need more help, or if you need help with something that you don't feel like you want to ask in class, come to office hours. So I've got office hours Tuesday and Thursday mornings and Friday morning. And that's going to be the other option you have for getting help. There's also a Discord server. And if you're in 224, you know about the Discord server. So that's you know, informal, it's unmoderated, it's not an official part of the class. But it's a place students hang out. Students from this class, students who've taken this class before will be on there sometimes. And you know, if you're stuck with something, it's like, I don't understand what the Sentinel node is about, right? And you've heard me describe the Sentinel node 10 times and it's not clicking. Maybe somebody else, you know, will explain it a different way that'll make more sense. And so you're free to use Discord to have discussions about the material in general, the concepts, and so on and so forth. But be careful about doing things like, you know, my code's not working, can someone take a look at it for me? Yeah, sure, I'll help you, send it over to me, right? Try to avoid that. Because that can circumvent your own learning, your own understanding, and there are well-intentioned people out there who will give you more help than they probably should, because, you know, it's fun to help people. But feel free to use Discord for sort of more general things, right? Understanding the material itself, but not so much for, you know, I'm getting this error and I don't know why. Can somebody tell me? Well, that's debugging, right? Which is an important skill to develop. And you know, I'm having trouble understanding how to use the debugger. Yeah, get some help with that. Can someone debug my program for me? Probably not a good idea. All right. Your last option for getting help is to email me. I'll probably do emails once a day, and I'm not going to be able to do emails with a lot of back and forth. So don't send me your code and say, I'm getting a syntax error. What's wrong with this statement? Well, maybe I'll answer that question, and I'll say, you know, you forgot a semicolon at the end. And then you're going to come back and you're going to say, okay, well, I put that in, but now I'm getting this other error, right? That's the end of the email conversation. At that point, we need to talk in office hours, right? So if we're going to have a back and forth dialogue, can't really do that through email. And I'm trying to get a handle on the situation where I was dealing with, you know, over 100 emails a day towards the end of fall quarter, and it's just not practical. So try to make use of office hours, Tuesday, Thursday, and Friday mornings. Linux, so we're working in a Linux environment. That's the best place to be doing programming right now, because we're doing C and GDB and Valgrind and all these other tools. So you want to work in a Linux environment, you can do that on the Linux server, linuxengrcs.com, or you can set up a virtual box if you're running Windows or OS X and install Ubuntu on top of that. And either of those are good options. Git, as I said, we're not using Git as part of the course, but I encourage you to continue to use it on your own. Keep track of your source code, track your changes, be able to roll back, be able to recover if you lose your files, and so on and so forth. Valgrind is a way to look for memory leaks, and we'll talk a lot about memory leaks in a few days. And Valgrind's a nice tool to help us understand how we're managing memory. One-day programs, as I said, I'm not doing one-day programs this quarter. Attendance, I'm not factoring attendance into your grade. I may note attendance from time to time. And for the in-person courses, I'll probably take attendance some days just for contact tracing and such. But it's not going to be a factor in your grade. Academic honesty, we talked about. Late work, so total of 4 slip days, right? All right, different way of doing slip days. So since we're not doing Git, we're submitting through Canvas. If you submit your assignment on time, then, I'll grade that assignment you submitted and there's no slip days used. If you want to turn an assignment in, a day late, turn it in a day late. And you'll be charged a slip day automatically. You don't have to tell me that you're taking a slip day. You don't have to ask permission. You don't have to apologize. You don't have to do anything. Just use the day. Once you submit your assignment to Canvas, that assignment is submitted. And you can't resubmit. If you resubmit, I'll ignore it. I'll grade the first one that you submit. So make sure before you submit to Canvas that this is the thing you actually want to turn in for grading. And once you turn something into Canvas for grading, that's the version that I will grade. And if it was turned in late, that's the number of slip days that you'll get charged. So if you don't want to turn an assignment in, if you're like, yeah, I didn't really do a good job on this, I'm not going to bother turning it in, don't turn it in. If you turn it in 4 days late, you'll get charged 4 slip days. Right? So this is all totally in your control. I'm not involved in any of this. You don't have to email me. You don't have to tell me about this. Just turn it in when you're ready to turn it in, or don't turn it in if you don't want to turn it in. And just be aware that once it's uploaded to Canvas, that's the version that I will grade. So don't turn in your assignment on time and then email me later and say, oh, ignore that one. I'm going to take a slip day and turn it in tomorrow. You do not have that option. Okay, is that clear? So turn it in and you're good to go. And then just a little table here to kind of help clarify this, right? If you turn your assignment in on time, there's no slip days. If it's late but less than 24 hours late, you get a slip day if you have at least one slip day available. So if you turn it in 10 minutes late, it costs you a slip day. If you turn it in 23 and a half hours late, it still just costs you 1 slip day. 24 to 48 is 2, 48 to 72 is 3, 72 to 96 is 4, and you can't turn it in more than 96 hours late. All right, and again, as I mentioned last quarter, slip days, they're really meant for kind of emergencies, unexpected things. Like, you're planning to turn your assignment in and the power goes out in your neighborhood and your laptop can't get on the internet and you can't submit this assignment on time, right? Use a slip day. It's there for emergencies when you can't make the actual deadline. But if assignment 1 is due next week and you're like, I don't feel like working yet, I'll just take some slip days, right? Then, if the power goes out at the end of the quarter and you can't turn your assignment in, you don't have the slip day available. Oh, thank you.
Oh.
Awesome. Thanks. So try to bank them and keep them for emergencies. You do not get to grade them, to cash them in at the end of the course, though. I had some students who wanted extended time on the final because they hadn't used slip days, and I can't do that. But, keep them in case you need them. All right, and other policies, may change over time. I'll announce them in class and try to put them on Canvas. All right, any questions on any of that stuff?
So, you're not doing the 10 minutes per minute over the due date of the final exam this time?
Oh, I don't know. I mean, that's not really a way to be able to get more time on the exam, right?
Right.
It's really just a way to say, if something messes up and you turn it in 5 seconds late, you don't get a 0, right? It costs you 10 points, which is better than costing you 100 points. But it was really just kind of a stopgap if something went wrong with the upload. So yeah, I'll probably do something like that, but I'm assuming people will be able to turn in their exams on time this quarter. All right, Zoom meeting info. Everybody's here. You know about Zoom. Office hours. Go to enjrcs.com/schedule. Same as always, and click through on my hours. And so, you know, Tuesday 8 to 10, and there's the Zoom info. And it's shared between all my classes and my office hours for advising. So there's a waiting room. If you connect and I don't take you right away, you'll sit in the waiting room and I'll get to you in turn. Link to the lecture video. So this is a YouTube channel that has all of the videos for all of my computer science engineering courses this year. So beginning with 224 in the fall, but at the bottom you'll find 222 and 215, and then 222B, which is what this section is called, or what I call this section. Those videos will be posted as well. There's also a link to the page of topics. So if you're looking for something in particular, like, you know, what did he say about uninitialized pointers? Well, you know, there's a topic of it 57 minutes in on this video. So you can follow that. And if you go to this video, these links are clickable. And if we have any shared code that we develop in class and that looks useful, I'll go ahead and post that. And you can get to that through this link. All right, additional C books. So I've mentioned this one in 224. This is a book that I wrote a few years ago, specifically for CSE224 and CSE222. And it covers some topics in C programming that you may find helpful in this course. So, you know, input and parsing and string processing, we talked about those in 224. There's a chapter here on pointers, right? So what's the whole idea with the ampersand and the star and arrays and malloc, right? So those you know, 10-page summary of pointers, basically. This probably won't teach you these concepts if you've never dealt with them before, but if you're working with them and you're trying to understand them, this is a different presentation that might help you nail down the concepts. Same with bit flipping. This will pop up a little bit in this course. It'll pop up more in other courses. There'll be a lot of recursion in this course. This is a different way to think about programming, and so there's some information in here that might help you with that. So feel free to take a look at that and you know, use it as it seems useful. All right, how-tos from 224. So if you were not in CSE 224, take a look at this page. It will tell you what the Linux server is, linuxenjrcs.com, your username and your password, and it talks about different ways to connect to the server from different machines. And it is very different from the CTEC server that you use in 121. So don't try to use CTEC, and don't try to use your CTEC username and password and so on if you want to get to the Linux server. So you can read through this, and it's just kind of a quick start guide, as well as some kind of general information about getting going in a Unix environment. All right, quizzes. So we've got several quizzes. There's due dates on those. You can do these any time that you like throughout the course before the due date. And quiz 1 is just, you know, the one question quiz to make sure that you understand that there's quizzes. 5 programming assignments, generally due on Fridays. And I will post this first assignment later on today or tomorrow morning. Programming assignments are due at 8 a.m. All right, so make sure you note that submission time. And then service learning project. If you were in 224, you started in SLP already. So we're going to continue that throughout this course. You're going to do a final upload week 9, which will be another poster showing your progress through the quarter, and then we're going to have an online presentation last Tuesday of the quarter. More details coming on those. If you were not in 224 in fall term, read through this. This basically talks about what a service learning project is, and it tells you how to submit a proposal. And so in the next 1 to 2 weeks roughly, read through this, figure out what kind of project you think you want to work on, write up a proposal, and send it to me as a PDF. And we can talk about it and sort of work out the details. If you were in 224, you already spent, fall quarter beginning a project, picking a project, making some initial progress on it, and so on. All right, and finally, midterm and final. So the midterm is in class. It's on Thursday, February 3rd, from 1 o'clock till 1:55. And you have to take it during class time. Okay, it's not something you can just take anytime you want during the day. It's in class during the regularly scheduled class time. And then the final exam is on the 17th, 1 o'clock to 2:50. That's the regular exam period set aside by Clark College for classes on Thursdays at 1. Important thing to note about the midterm will be closed book, closed computer. Okay? The only thing you get to use during the midterm is your notes, and you can have 6 double-sided pages of notes or 12 single-sided pages. They can be handwritten, computer printed, typed, whatever you want, roughly, letter size or A4 or smaller. And you're going to basically hop onto Canvas to see the questions. You're going to write up your answers by hand, and then you're going to scan those and submit scans as a PDF. Okay, so you're not allowed to use your computer during the exams other than to read the questions and to upload your PDF of the answers.
Quick question.
Yeah.
Is this something that you want handwritten, or is this something that you want typed?
It's going to have to be handwritten because you're not allowed to use your computer.
Okay.
I mean, you could typewriter it, but but yeah, handwritten.
Is this like last time where you pull it up and read from there, or do you want like print it out and then us write it on the paper?
You can read from Canvas and you can write it out on paper, or you can print it and write your answers on the page. But since not everybody has access to a printer, and I don't want people to require that, I would say just go ahead and write your answers on paper and scan that and upload it.
Another question.
Mm-hmm.
This is certainly very different than your other ways of doing midterms and finals. Is it just because the content is much different?
It's mainly because of slippery slopes. Because I've when we were entirely remote, people were using Canvas to take the exams, which is fine. But my hope was that and my intention was that students would basically be using a plain text editor, Notepad or VI or something, to write up their answers. And over time, more and more students have been doing more and more things on a computer while they're taking the exam, up to and including, when I asked questions about what would this piece of code do, people were actually typing that code into the server during the exam, running it, and then writing down what the code did. And that's not the intent of these kinds of questions. So I'm just putting, a very clear, unambiguous requirement on here, which is you cannot use your computer for anything other than reading the questions on the exam and uploading the PDFs. And I just want to remove all ambiguity so that if there's, an incident in the future where somebody is typing in code during the exam or something, I can clearly say, okay, that's not allowed, that's a 0 on the exam. So it's just kind of trying to remove any potential ambiguity or confusion.
Oh, thanks.
Yeah. The SLP presentation, somebody said of my peers in the other section, how can we present? So we'll talk about the presentation more in a few weeks, but it's going to be one presentation across all sections of 222 and also across Izad's sections of 252, his engineering courses. And it'll be one big expo, and it's usually from 3 to 5 on that last Tuesday of the quarter. And it'll be online. And so it doesn't matter if you're working with somebody in a different section, you'll both be at the presentation. All right, and then final exam is exactly the same format as the midterm, 6 pages of notes, so on and so forth. All right, any questions on any of that? Awesome. I think that's it for kind of the administrative stuff. Last comment is, you know, this is a 2-hour class, so we'll usually take a break halfway through. So 1 o'clock till I think 3:05 or 3:10. So we'll probably take a break around 2 o'clock each day and just kind of, you know, stretch our legs and rest my talking. Cool. All right, let's talk about data. Computers, right? Computer programming. You write a program, you're basically creating a set of instructions, which you're telling the computer what to do. And there's 2 pieces to this, right? There's telling a computer what to do. I want you to do some multiplication or some addition or copy something, right? And there's telling it what to do that thing to, right? So it's like a verb and a noun. And so we can think of this as code and data. And code is, you know, the set of instructions, and data is the set of things that those instructions work on. And in C, our data takes the form of variables. So I might say I've got an integer I, and I've got a character C, and I've got a double called X and Y and Z. And you know, you make a statement like this that declares a variable, and now you've got a variable, a piece of data that you can manipulate in your code. And that's great, that works fine for small programs and for small amounts of data. But what may happen as we develop more complex programs is we find that we have a lot of pieces of data that all kind of belong together. For example, these 3 things might be the x, y, z coordinates of a point. And that point might be referenced by some internal count that I call I. And I might have, you know, some sort of label associated with that, which is in the form of a single character. And so, you know, I've got an integer, a character, and 3 double precision floating point numbers. But they're not just 5 separate variables. They all kind of go together. And so what we want to start doing is adding some sort of structure to our data. And one way we can do this in C is, you know, with a struct statement. So we can say something like struct, you know, my data. And then we can say, you know, well, there's an integer I. Hopefully we would be using better variable names than I, C, and X, Y, Z. But when we do this, we create a new type of variable, right? So we create a variable that we can think of as a type my data, and now I can say something like struct my data point 1, and point 1 is not just an integer or a double or a character, it's all 5 of these things. and I can say, okay, I want to look at point 1 dot I and set that equal to something, and I want to take point 1 dot x and multiply by point 1 dot y and do something else, right? And it's this enhanced type of variable. And so this is one way to add structure to the information in our program, is to group it together into this sort of single logical entity. And that's a direction we'll explore a lot in spring when we'll talk about object-oriented programming. And in that mindset, this might be called an object. It's a thing that has a bunch of different pieces to it. But in C, we just call it a structure. So this is a structure called my data, and it's got these 5 elements to it, these 5 fields. So that's one sense in which we have structure associated with data. Right, and this is a data structures course, so this is a good thing. Another way that we sometimes group data together, that we add structure to it, is by using an array. So for example, let's say I'm writing a program that takes in student scores and records them and does some calculation and comes up with, course grades or something like that. So I might have, an array called grades. It's an array of integers that has 100 elements. And now grades bracket 0 is the grade of the first student, student 0. Grades bracket 1 is the grade of the next student. Grades bracket 2 is the grade of the next student. I don't need to use an array. I could call my grades, A, B, C, D, E, F, G. And the first student, I could store their grade in A. The second student, I could store their grade in B. But that's a real nightmare code-wise. Because now when I want to take the average, I have to, take the average equal to A plus B plus C plus D divided by 4, right? So to avoid that, right, we structure our data in a way that respects the relationship among these different pieces of data. In particular, the fact that these 100 pieces of data are all grades corresponding to 100 different students. And these students might have, information about how many slip days they've used. So I might have another array called slips, or slip days. And rather than call my slip days, PQRSTUVW, I'm going to put them in an array called slip days. And there's additional structure here. If I'm writing this the way most people would write this, grades bracket 0 is the grade for one particular student. Slip days bracket 0 is the number of slip days used by that same particular student. In other words, grades bracket I and slip days bracket I go together. And maybe I have an array of names. And same thing, names bracket 0 is the name of the student whose grade is in grades bracket 0, who has used a number of slip days given by slip days bracket 0. So we already do some sort of organization of data when we use an array. We're already, playing off this idea that these pieces of data belong together and that there's an organization. It's not just, 300 random pieces of information, but that there's structure there. All right, so that's what we've been doing so far, right? This is our understanding of variables and structures up to this point. So yeah, someone said structs help with the abstraction so that all the data can fit together. That's a good way to put it. All right, so let's do a 5-minute break. And we'll come back at 2:05, and then I want to start digging into what we're going to do beyond this, and start looking at data structures in the sense of CSE222. All right, so we'll come back in 5 minutes. All right, welcome back. Let's see. So, quick sidebar. So, remember when you're logging into the Linux server, your username is your first initial followed by your last name. There's no period between those. There's no number at the end. It's just first initial followed by last name. That's different from the CTEC server, which was CSE222B. So make sure if you're trying to log in, you're doing first initial last name, and going from there. All right. So when we make arrays, remember arrays in C, we're dealing with pointers. Right? When we make an integer, grades bracket 100, grades is actually a pointer to an int, whatever the heck that means. And when we have structures, like, a struct my data, that's a lot of pieces of information. 3 doubles would be, 24 bytes, and a character and an integer. We've got a few dozen bytes of information there. And sometimes when we want to pass a bunch of information from one function to another, instead of passing all of those bytes, what we do is we pass a pointer to that structure. And we're going to do that a lot in this course. So all of this is a way of saying that basically we need to talk about pointers. And pointers are an essential part of this course and any data structures course. So let's dig into pointers and let's demystify these and try to make peace with them. So I'm going to draw a kind of imaginary memory map of a computer. And this is a non-realistic memory map. This is very simplified. Most computers don't have a memory location 0. Small ones like PIC processors do, but most machines we deal with, memory locations 0 and such don't exist. But we're going to use a simplified version of memory. And let's suppose in our C program we say something like integer n. Alright, so what happens when the compiler sees this line that says integer n? And the compiler, remember, it takes your C code and ultimately it creates an executable program. And that executable program gets loaded into the memory, the CPU points to it and starts executing, and it runs, whatever instructions the compiler created. Alright, so in a C program when you say integer n, the main thing that happens is the compiler says, hey, I need somewhere to store an integer. And combination of the compiler and the linker will work together and eventually decide where that integer is going to be stored. And it's going to be stored at some particular location. For example, let's just suppose that n is stored at location 4 in memory. Alright, so anytime our program tries to do something with the variable n, it's really going to be doing something with location 4. And it can be useful in this course to start thinking more about what's going on in the computer from the perspective of the CPU instead of the perspective of the programmer. The programmer has an integer called n. The CPU knows about a location in memory with address 4. And what's in that location? Well, I have no idea. We don't know what's in any of these locations in memory, because memory is just kind of uninitialized. So if I were to print n, and this is pseudocode, right? It should be printf and so on. But if I were to print n, who knows what would be printed? Might be 0, but probably not. It's probably going to be some weird number because we don't know what's in location 4. But this print statement is going to compile into code that basically says, hey, read what's at location 4 in memory and let's print it out. And it'll print out, some weird number. Now if I say n equals, 2, the code generated by the compiler will do the following. It will say, hey, let's take the bits corresponding to the number 2, and let's store those at location what? Location 4. And so this location in memory is going to have a 2 in it. And now if I do the same, print n, the print statement, the code in the print statement will say, okay, let's go to location 4, see what number store there. It's a 2, and it'll generate the ASCII codes for a 2. And we'll see a 2 print out. Alright, so those are plain variables. Those are just, integers, characters, things like that. Now suppose I say integer star p. So I'm making p to be a pointer to an integer. Well, p is still a variable. It's got to be stored somewhere in memory. Where's it going to be stored? I don't know. Maybe the compiler linker decide we'll store p at location 1. And again, the value stored at that location, who knows? Could be anything. So if I print p, I'll print, some random number. Now, if I were to do the following, suppose I were to say p equals 4. And my compiler will complain, up and down if I actually try to do this. But suppose I execute a statement that says set p equal to 4. Okay, p is stored right here. That's going to put a 4 in this location. Well, if I print p, it's going to go to location 1 where p is stored. It's going to find a 4. It's going to print out a 4. But suppose I say print star p.
That's going to print the memory location, right?
Yeah, so let's spec out what exactly this means. So star p, this means the thing that p points to. In other words, not p, but the thing stored in memory at the address given by p. So if I just print p, I know that p is stored right here. I'm going to print the thing stored right there. But if I print star p, there's one level of indirection that takes place. The system says, okay, let's look at the value of p. That's a 4. Let's print what's at location 4. And so this will print 2. That's all there is to pointers. It's one level of indirect reference. If I print p, it's just going to print a 4. If I print star p, it's going to print what's at location 4. It's going to go to location 4 and say, oh, there's a 2. It's going to print out a 2. That's the whole magic of pointers.
And I know this is a very basic idea of pointers, but like in this case for integer star p, why would you not just put print in? Like, why would you want to indirect?
Well, so for this example, right, it's a silly thing to be doing this, but
sure.
As we develop data structures, what we're going to be doing is basically creating variables while our program is running. And in 224 and most other programming that we may have done up to this point, every variable that our program is using is declared somewhere. Every integer is declared integer such and such. Every character is declared character such and such. But as we get into more complex programs, we're going to create programs that work with variables that don't exist when the program starts. We're going to actually create these variables while the program is running. And that's the real power of data structures, right? So the bytes are allocated during runtime. And so in that case, right, we might not even have an integer n. we might only be able to get to this because we've set a pointer to point to some location in memory. And this will be a lot clearer / confusing when we talk about programming assignment 1 on Thursday.
Alright.
Right? It will answer the question, but it will raise lots of other questions.
Well, when 4 is an integer value, how would it recognize it as an address value?
If I say print star p, that's what it will do. It will try to treat 4 as an address. And we don't usually, say something like p equals 4, but if I were to set p equal to, something that actually was the location in memory, then this is exactly what would happen. When I print star p, it would say, okay, what's the value of p? Let's go to that location and print out what's stored there. But yeah, it's kind of a cherry-picked example so far. But we'll make it more realistic in a minute. Alright, so is this making sense so far? Why star p is going to print out a 2 in this case.
Yes, but could you put up that other piece of paper that you had with like the meaning of it all?
Oh yeah.
Because you had it up and then you kind of took it away real fast.
Sorry about that.
Thank you.
Alright. So star p means don't use p, treat p as a memory address, and use what's at that address. Alright, so suppose I also have, an integer j, and let's say j is stored at location 8, and I set j equal to 42. So there's a 42 stored right here. Alright, so I can use an ampersand, and an ampersand does the following. So if I say ampersand some variable name, that means the location in memory where that variable is stored. So ampersand variable means the location where that variable is stored in memory. So now if I were to say something like p equals ampersand j, what's the compiled code going to do? It's going to say j is a variable, ampersand j, where's j stored in memory? And it knows j is stored at location 8, that's going to set p equal to 8. And so it will go to the location where p is stored, which is up here, and it'll say, hey, let's set that equal to 8. So ampersand variable, we call this dereferencing a pointer, says, hey, use that pointer's value as an address and tell me what's stored at that address. Ampersand is kind of the other direction. It says, hey, tell me where this thing is stored in memory. So if I say p equals ampersand j, in this case, p is now equal to 8, because that's where j is stored. And now if I say print star p, exactly the same thing as before. The code will say, okay, p is a variable. Where is it stored? It's stored right here. Let's see what the value of p is. P is equal to 8. I'm not going to print an 8. I'm going to do something first. I'm going to take 8 and use that as a location in memory. I'm going to go to location 8, see what's there. 42. I'm going to print a 42. So this will print 42. All right, if you've done Engineering 270, this is the indirect file register thing. If you load a file select register, this is what INDF0 is. It's saying, hey, don't give me the value of the file select register. Treat the value of the file select register as a memory location and tell me what's at that memory location. So when we do star P, sometimes we call that dereferencing. A pointer. The idea is P is a reference to another location in memory. Dereferencing means, hey, tell me the thing that P is pointing to. Tell me the thing that it's referring to. All right, so here's the goody part. If I say something like star P equals 7, what does the compiled code do? It says, okay, first of all, P is a variable. Tell me what its value is. Its value is 8. Okay, I'm not going to set this location equal to 7. I'm going to use 8 as a memory address. I'm going to go down to memory address 8. That's what I'm going to set equal to 7. So if I say star P equals 7, it says P is a pointer. Where does it point? Points to location 8. I'm going to set location 8 equal to 7. And it'll change this. If I just say P equals 7, it would write a 7 here. If I say star P equals 7, it comes here, sees that 8, and says, okay, I'm going to change what's at location 8. All right, if you've got that, you've got pointers. That's all there is to pointers. The star says use this as an address. The ampersand says give me the address. And most of the challenge in this course is not, trying to understand what a pointer is. It's figuring out how we want to use pointers. But before we get to that point, the big hurdle is, trying to understand this star and this asterisk business. And it can be confusing. It can flip back and forth and so on and so forth. But eventually we'll have a pretty solid understanding of this from experience. And then we'll mostly be working with how we want to use these mechanics. All right, so let's hop into GDB and play with some of this in code. So I'm just going to write some junk code here. Oh, and someone asked in chat if we're going to spend time talking about void pointers. Pointers point to something, and they usually point to integers or characters or maybe other pointers or things like that. But they can also be declared to point to void, which basically just means that they're not pointing to anything in particular. It's kind of a nod to the compiler to keep it happy. But it's a pointer is a pointer is a pointer no matter what it's pointing to. It's really just a memory address.
question.
Yeah.
When's assignment 1 going to be available to do?
Probably tomorrow.
Okay, thank you.
Yeah. All right, so here's some test code. I've got an integer I, I've got a pointer to an integer p. I'm going to print out the value of I. I'm going to set I equal to 5. I'm going to print the value of I again. I'm going to print the value of p, and I'm going to print the value of star p. And we're just going to play with this in GDB. So we'll compile it with a -g switch. We're going to ignore the warning because I know why it's giving me the warning and I want to ignore it on purpose. And let's not use bracket bracket for now. Someone said star p equals p bracket bracket. Correct. P bracket bracket is a different thing, and I'm going to say let's just ignore that for now and let's stick with star p. Alright, so I'm going to compile with a -g switch, which says include debugging information. And I'm going to debug it by saying GDB and then the name of the executable. I'm going to say start. Okay, so remember, GDB shows you the statement that's about to be executed. So it's about to execute the statement which says print the value of I as an integer. So I'm going to say next, or n, which says go ahead and execute that statement. And it prints out the value of I, and it says I equals 32767. Well, that's a weird value, right? It's actually not that weird. But you know, I never said set I equal to 32767, but that's the value of it anyway. And you know, if I print I can see it's 32767. It's because I has not been initialized. But now I'm about to execute the statement which says set I equal to 5. And so I'll execute that. And it prints out, you know, well, it doesn't print out anything, but if I print out the value of I can see that I is equal to 5. So now if I run this print statement, it'll print out I equals 5. Alright, so that's just declaring an integer, seeing that if we don't initialize it, it has a potentially random number. And then if we give it a value and we print it, of course, it's got that value. Alright, now we're going to print the value of p. And when I execute that statement, it didn't print anything. And this is important to note. So suppose I didn't run this in GDB. Suppose I just ran this from the command line. I would see I equals some number, I equals 5, and then segmentation fault. And if I look at my source code, I say, you know, I printed out I equals, and I got that weird number, 32766. And then I set it to 5, and I printed it out again, and it said I equals 5. And the next thing it did was seg fault. And if I'm not careful, I'm going to assume that my seg fault came on this statement, because it never printed out what p was equal to. But that's a red herring. This statement does not cause a seg fault. But this statement also does not generate any output. Any idea why?
Because you declared it as a pointer to p and not p itself?
Could be, but that's not actually the case. Something much...
And you haven't given it a value, right?
Haven't given it a value, but you know, I didn't give I a value, and it still printed it out. It should have some value. I should dereference it, but if I don't, it should still print something. This is a red herring. It's actually got nothing to do with pointers. But it's something we have touched on in 224.
Is it because... Does it have to do because it's looking for a decimal and it's not a decimal?
That could also be a problem, but it's not the problem in this case. This is really subtle. I did not print a new line at the end of this. And remember, in C, your print statements are buffered. And so even though I said print out p equals a decimal value, that got printed, but it didn't actually show up on my screen because that output is buffered. and most operating systems buffer output until there's either so much output that it needs to force it all out, or you print something like a new line. And so I might spend, you know, a few hours trying to figure out what's wrong with this print statement, when in fact there's nothing wrong with it. This statement executed correctly, and this next statement is what generated the seg fault. So here's all I got to do. If I go up here and I put a new line at the end, right, I can see clearly that it did print the value of P, and then it got a seg fault, and that correctly shows me, hey, this statement executed, this one generated a seg fault. So that's just one of those things that can cost you like a lot of hours and a lot of frustration. Always, 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 when you're writing debug statements, put new lines at the end of them. Right? Even if you want your output to appear all on one line, put the new line in there, because it will force the output to be flushed immediately. All right, so I mentioned that for what it's worth. So let's go ahead and run this in GDB again. And let's start it and let's work through. So I set I equal to 5. There's the print for I equals 5. I print the value of P, and P is equal to 0. Now I'm going to try to print the thing star P. And remember what this means. This means let's go to not P, but the thing stored in the memory location at the address given by P.
So in this case, it's going to go to memory location 0, right?
Exactly. It's going to print the contents of memory location 0. And when I try to do that, I'm going to get a seg fault. And if I print P, I can see it's a 0. If I try to examine memory location 0, guess what? Cannot access memory at address 0. Because on purpose, memory location 0 does not exist.
Null pointer.
Null pointer. So this is where most seg faults come from. This is where most of our seg faults in 224 came from. This is where almost all of our seg faults in 222 will come from. Trying to use a pointer that hasn't actually been set up to point to anything.
So that's one of those things, pretty much no matter what, unless you initialize that variable to something other than 0, you will get a seg fault.
Pretty much, yep.
Okay.
And the reason they do that is because one of the most common mistakes a programmer can make is failing to initialize a pointer. So if pointers start off at 0 and you don't give it a value that's meaningful, you're almost guaranteed to seg fault the first time you try to use it. And that's better than hitting some random location in memory and going ahead and continuing to run, but secretly corrupting other data in the process. And then eventually down the road, you know, something blows up and you have no idea where it went. All right, so how can we fix this? Let's go ahead and set P equal to ampersand I. Let's set P equal to the address of this integer I. And now I'm going to print out P again after we've done this, and I'm also going to print out star P. Alright, so we're going to print the initial value of I, which is uninitialized, so it's 21,845. We're going to set I equal to 5, print out the value of I again. I is equal to 5. So the universe works. That's always good. And now we're going to print the initial value of P. It's negative 7104, just some weird number. Now I'm going to set P equal to ampersand I, the address of I, and if I print P again, it's got a different value, negative 7348. And if I print star P, it means go to that location in memory, tell me what's stored there. Guess what? It's the number 5. Why is it 5? Because P is pointing to the variable I, and I has a value of 5. So this is the GDB version of what we were doing on paper here.
And the negative 7,000, that's just such a big number that the 2's complement is like a negative, right?
Exactly. It's such a big number that it's coming out negative. Slightly negative. Now, if I know that I'm dealing with a pointer, right, when I try to compile, I'm getting these warnings about, you know, %d expects an int, but I'm passing it a pointer. If I want to print the value of a pointer, what I can actually do is I can print things out with a %p, and that'll put my variable in hexadecimal format, and it will make it big enough based on the operating system I'm on. Memory addresses on this machine are 48 bits. So we'll print this out as a 48-bit number as 12 hexadecimal digits. So I'll print out p as a %p, I'll change it to %I, print out %p, and go on from there. Alright, so let's print the initial value of p. It's big long hexadecimal number. 7 followed by a bunch of f's followed by some other stuff. And then I set p equal to %I, and if I print p again, it's 7 followed by a bunch of f's followed by E3, 4, C. And if I look at this location in memory, well, there's a 5 sitting there. That is the location where the variable I is stored. If I print %I, it's that address. So that's an actual address in memory where this variable I is stored. When I set p equal to that, p is pointing to this location in memory. Well, that's an I. If I were to store a different value in this location, the value of I will change. So let's do that. Let's set the thing at location, the location pointed to by p, let's set that equal to 42. And then let's print out the value of I again.
You have to put those parentheses there in order to...
I put them in there just to be unambiguous, to make sure it's clear to someone reading this that $p is the variable. But it will figure it out if you leave those off. Alright, so I is equal to 5, right? I've set it equal to 5. I'm printing the value of I. It's telling me I is equal to 5. So clearly that's the value of I. Alright, now I'm going to play around with p. I'm going to set p to this number. And now I'm going to say $p equals 42. Now before I do this, I can double check the value of I is still 5. But as soon as I say $p equals 42, the value of I has suddenly changed to 42. Why? Because $p is I. Right? Because p is equal to this value. $p says, hey, I want to work with the thing stored at this location in memory. Well, that location in memory is the location where I is stored. So I've got two things referring to the same spot in memory. I've got I referring to that location, but I also have $p referring to that location. So if I change $p, I change I. If I were to change the value of I again and then look at $p, it would be whatever that new value was that I stored in I. They're both referring to the same thing. And that's a huge, huge concept for dealing with pointers. And this is not at all obvious from looking at the C code, but it's fairly obvious if you're thinking of it in terms of memory locations. If I'm thinking I is a variable stored here, and p is a variable equal to this, and $p refers to this location, then it's fairly clear that $p and I, are interchangeable. So this is one of these cases where sometimes you want to think of it high level from C, and sometimes you want to think of it lower level from the perspective of memory and what the CPU is doing. And we'll bounce back and forth between those levels a lot. And that's part of the discipline of working with data structures, is being able to look from these different perspectives. All right, questions about this?
Definitely something to rewatch again.
Okay, yeah.
Mostly I want to play with the code.
Yeah, definitely something to play with.
Interesting in concept.
Mm-hmm. And this is, a pretty short program, and a lot of these print statements we don't even need. It's really, this and this and this that are most interesting. And if we're in GDB, we don't need all these print statements. We can always, print out star P or ampersand P or things like that. And as we develop our programs, like for PA1 and moving forward, you'll necessarily be spending a lot of time in GDB. Because, as we said over here, right, the real magic is going to come from the fact that eventually we're going to create variables on the fly while the program's running. And we're not going to be able to say, print I, for example. The only way we're going to get to some of our variables is by saying something like, hey, P is pointing to this variable. Let's see what it's pointing to and what's stored at that location. And when things go wrong, it's often going to be because this is pointing to the wrong spot, or we didn't use the thing that was pointing to the right spot. And those kinds of issues will become more apparent if we're stepping through our program in GDB and constantly making, our own memory map to see what's where, and comparing that to what we think is supposed to happen. So, P is equal to this. Where is P stored in memory? Well, it's stored at this location. It's pretty close to, where it's pointing to right now, which is the value of I. In fact, it's right next door to the value of I. And let me just spec this out for future reference. So when I print ampersand I get 7 a bunch of F's and E34C. So I'm going to draw a memory map on paper and I'll switch over to it. So E34C is I, and then 7F E350, that's where P is stored. So our simplified memory map looks something like this. So counting in hexadecimal, 4C, if you add 4 to that, you get 50. This is for C, D, E, and F. This is 50. So there's actually 4 bytes associated with this. Well, that's because integers take 4 bytes to store. An integer is 4 bytes. The first byte is stored at location E34C. The next byte is at 4D, and then 4E, and then 4F. And so if we say examine byte, this location, there's a 5 stored there, and then a 0, and then a 0, and then a 0. So that's the value of I. The next location, E350, that should be where P is stored. Well, E350 contains a 4C, followed by an E3, followed by an FF, and an FF. That's where it's storing this number. There's the 4C on the right side, there's the E3, and then the FF. There's another pair of FFs, and then a 7F. And then a few zeros. So you can actually look in the memory of your machine while your program is running and look byte by byte into the main memory and see which bit patterns are stored where. And sometimes we're going to need to do that. That's going to help us understand what our code is doing. If you have VirtualBox and you install a 32-bit version of Unix, these addresses come out a little nicer. They end up being 32 bits instead of 48. But you get good with copy and paste, or you get really good at typing these. What is it about these 7 Fs? Why do all these addresses have 7 followed by a bunch of Fs? Any ideas what might be significant about an address like this?
The program memory, when a program is running, the operating system has to allocate some amount of memory, and it's probably going to be in the same general region, so like 7FFFF.
Mm-hmm.
With 7Fs.
Yeah.
So like in that general region is where all the bytes for the program will be.
Exactly. And if we take this number and we write it out in binary, right? This is the number 7. This is F. That's what 7 followed by 7 Fs look like. And then there's an E350 or an E34C or whatever. But the beginning of your address is this 0 followed by a bunch of 1s. And if we thought of our entire memory, this is just kind of a sidebar, if we thought of our entire memory as going from a bunch of 0s to a bunch of 1s, the spot right in the middle, this would be a 1 followed by a bunch of 0s. This would be a 0 followed by a bunch of 1s. And so these locations are situated pretty close to this halfway point. In other words, this halfway line, the address right before it would be 7FFF, FFFF, FFFF. And the point right after it would be 8000, and then 8 more zeros. And the reason our variables are sitting in that location has to do with something called a stack. And we'll talk about stacks in a few weeks. It's another kind of a data structure. And if you've done Engineering 270, you know what a stack is. It's exactly the same thing here. But a stack is basically an area of memory that starts off right here and grows in this direction. And it's a place to use for temporary storage. And the main thing we use temporary storage for in C programs is local variables. Well, if you look at our code, integer I, integer star p, these are local variables. They're local to this function called main. They only exist while this function is executing, and when this function exits, these variables no longer need to exist anywhere. And this area of memory is an area of reusable storage, where when we go into a function, we can allocate a chunk of space here to store our variables, and when we exit that function, when we do our return, we can reclaim that space and use it for other local variables for other functions. So when you're debugging, if you see 7 with a bunch of Fs, that's often a sign to you that you're looking at a local variable. All right, so let me clean up some of this code. And so if I write my code like this, where I just set star p equal to 42, I'm going to segfault. And the reason I'm going to segfault is because my pointer p has not been initialized. It's a 0. I'm going to try storing something in location 0, and that gives me a segfault. So if I try to, give this some location in memory, my compiler will complain. But I'll probably still segfault. Unless I happen to luck out and set p equal to a location in memory that actually exists, that I can actually write to without a fault. Well, if I want a pointer, I don't want to just try to guess a magic number. So a lot of times what we'll need to do is we'll need to find somewhere in memory where we can store something, some kind of variable. In other words, we're going to need to find an address in memory that's usable for storing information. And there's a function we can use to do that called malloc. And so if we want to use malloc, we have to include another library called standardlib. And instead of setting p equal to random number, we can just say malloc. And that will say, hey, find me a location in memory where I can store something. And then here we'll say, go ahead and store 42 at that location. And malloc needs an argument. It needs to know how much memory you want. And so I'm storing an integer that's 4 bytes. I'm going to ask for 4 bytes. So I said p equals malloc 4. If I print p, it's equal to some location. If I examine that location, it's got a 0 in it. But if I execute the statement which says star p equals 42, and now I examine that location, it's got a 42 in it. 2a is 42 in hex. And this location is not a 7FFF, it's a location that starts with a bunch of 5s. On this machine, these locations come from a different area of memory. It comes from an area called the heap. And heap memory, for whatever reason, starts, at an address that begins with a bunch of 5s. And if I were to malloc another 4 bytes, I'll get a different location in memory. I get 7FFF, blah, 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 1F10. If I call malloc again, I'll get a different address, 1F20, 1F30.
Out of curiosity, so malloc is just a randomization of placing memory?
More or less, yeah.
Doesn't it already randomize it?
Well, the goal is not to randomize it. The goal is to find a location that you can use. And it
Oh, so it just finds an empty parking spot.
It finds an empty parking spot, exactly. And it tells you what the spot number is. And in this case, it's finding a spot that's big enough for 4 bytes. It's actually big enough for 16. That's the smallest it will allocate. So if I ask for 16 bytes, it'll give me 40 and 50 and so on. If I ask for 17 bytes, it'll give me 70. The next time it'll give me 90. So it's allocating in chunks of 16 bytes at least. If I ask for 1700 bytes, I get a very different address. Because the memory I ask for is always going to be contiguous. It's going to be 1700 bytes, one after another that are all available. And we don't want to hardwire magic numbers like 4 because I happen to know an integer is 4 bytes. But on a different processor, an integer might be 2 bytes. It might be 8 bytes. Next week it might be 64 bytes. So instead of hardwiring something like the number 4, we use sizeof. And always, always, always use sizeof with a type of variable. Don't use it with the name of a variable. Almost guaranteed if you say sizeof name of a variable, you will end up with a problem in your code somewhere someday. If you use it with a type of variable, you're guaranteed to be getting the right thing. So if I want to allocate enough space for an integer, pass an argument sizeof int. If I want enough space for a double, say sizeof double. But don't say sizeof I, for example. It's a recipe for disaster. Here's another thing to keep in mind with this course and with the things that we're going to be doing in this course. It's very, very common, it's probably most common, that if you have a bug in your code, one of two things will happen. One, you will get a seg fault right away. Or two, you will not get a seg fault. You will not get an error, but you will plant a little bomb somewhere. And somewhere later on as your program is executing in some totally different section of your code, that bomb will go off and your code will blow up. And the problem's not going to be where the program was when it blew up. It's going to be somewhere earlier in your code's execution where something went wrong and it silently created this problem. I'm getting smiles from someone who's had this happen. right? And this is a classic way of setting up a bomb that will fail later on, which is to say size of variable name, for example. Can you not just do integer p equals malloc size of paren paren? I think size of needs an argument. And if it doesn't, I would put an argument in there anyway to make sure you know exactly what it's taking the size of. Size of is a compile time thing. It's not a runtime thing. It's not a function.
I meant like assigning it to a pointer there.
Yeah, you can do that. You can do integer star p equals malloc. And yeah, you can do that in one statement.
I did that with the Pascal's program. If you tried to go out too far, check if it is too big, it returns a 0 bytes allocated.
Oh, okay. Cool. Yeah, so malloc, if it doesn't have enough memory available, it will return a 0. So if I print malloc of, you know, some big long number, ooh, it actually did it. There we go. It'll give me a 0, which is its way of saying, hey, I couldn't allocate that many bytes of memory. And we'll talk about logistics of that when we get into more details of using malloc. Let's see, when you pass a variable to a function by reference, why is it that you're able to manipulate the variable in the body of the function? You'll be manipulating the memory address of the arguments passed. So when you... I don't want to go too far into this, but somebody just asked a question in chat. So if you pass, let's say you have a function whose argument is a pointer to an integer. Inside this function, if I say something like star n equals star n plus 1, and then in my main function I have, you know, an integer I, and I say function, and I pass the address of I. When I come back from this function, this local variable I will have been incremented by 1. Right? Because I passed the address of it, which means n is a pointer to this actual variable I. And when I said take the thing n points to, that's I, add 1, store it back in the place that n points to, that changes the value of I. And so when I call this function, the value of I, my local variable up here, actually changes. If I do something like, you know, n equals something, while I'm changing the value of n, that's not changing anything up in my main program. N is a local variable, but I'm using n to refer to a location, which happens to be the location of this variable that's part of main. We'll play with more with that another day inside GDB and see how that works. But that's why we passed, you know, ampersand variable to scanf, for example. Just so that scanf can actually manipulate the value of that variable because it knows where it's stored in memory. All right, so change of gears here. Let's motivate why we care about these data structures, why we care about dynamic memory. And this has to do with something called order of complexity. And order of complexity is a way of measuring the time complexity of an algorithm. How much time, in some sense, an algorithm takes to execute. And so it depends on the algorithm, right? But here's the thing. How are we going to measure how complex an algorithm is? Let's say we have two sorts, two different algorithms for sorting an array of integers. And we want to know which one of these algorithms is better. Well, there's a lot of ways to measure which one is better. So we could look at which one is more complex, which one has more lines of code. But that's not terribly interesting to us. You know, mostly we're interested in speed. We want to be able to sort as many numbers as possible, as quickly as possible. And we don't care if this algorithm has twice as much code to it if it runs 10 times faster. So we're looking at performance in the sense of time, but we're not really interested in just the raw amount of time that an algorithm takes. And that's because, you know, the amount of time it takes to sort a set of numbers depends on what kind of machine it's running on. If I'm running this on my laptop with 4 cores at 3 gigahertz, or I'm running it on my Arduino Nano running at 16 megahertz, or my PIC processor running at 32K, the same algorithm is going to take different amounts of time. So what we like to study is, if we have an algorithm and we look at an increase in data, what's the corresponding increase in time? So let's think about a sort algorithm. And suppose we double the amount of data. Well, a few things can happen. If it's a really, really fancy sort algorithm, it may not take any more time. That would be kind of magic. Something that can sort 1 million pieces of data as quickly as it can sort 500,000 pieces of data. It could be that the amount of time doubles. Twice as much data, twice as much time. Well, that would be pretty cool. And if we had 10 times as much data, maybe it takes 10 times as much time. And if we had 100 times as much data, maybe it takes 100 times the amount of time. Well, all of this looks like something linear. And we represent that by saying this is order n. And when we say order n, what we're saying is we have this kind of increase in time corresponding to these increases in data. It's linear. If our data n goes up by, 5, our time will go up by 5. But that's pretty unusual. A more common situation might be this, and this is what a bubble sort does, for example. If we double the amount of data, it takes 4 times as long. If we have 10 times as much data, it takes 100 times as long. If we have 100 times as much data, it takes 10,000 times as long. This is like a square or a quadratic. This is what we call order n squared. That's a bubble sort. This is something we can probably live with.
Hold on. What was a bubble sort?
N squared. So if you actually work through the code for a bubble sort, it's a pair of nested loops. And it goes through the inner loop and the outer loop roughly n times. So if I double n, well, it does the inner loop twice as many times, and it does the outer loop twice as many times, and for each pass of the outer loop, it does twice as much work with that inner loop. So it ends up being 2 times 2, 4 times as much work. And so more or less, first order approximation, when you increase your data by n, you increase the amount of time by n squared. So we would say that algorithm has an order of complexity of n squared. Or we could say it's an order n squared algorithm.
Do we try to avoid bubble sorts for this reason?
Yeah, bubble sorts are fine if you're doing a small amount of data. But if you want to sort, 1 billion pieces of data, it's going to be a really ineffective sort. But there's worse things. There's order n cubed. Some stuff you'll do with matrices, like trying to multiply matrices, right, can become an n cubed, or trying to find inverses of matrices. There's things like order n to the n. There's order n factorial. These are really, really horrifying orders of complexity. And yeah, this is generally worst case.
Could you treat it as a rule of thumb that nesting for loops generally leads to the exponent of the order? So like
Pretty much, yeah.
For loops brings you to like order n4.
Yeah. Yeah, if I had 4 nested for loops, it would probably be at least an order n to the 4th. Could be worse. That's assuming each of those loops runs about n times. So there's also algorithms that are better than this. A common algorithm that we see in this class will be log n, or maybe n times log n, or log of n squared, or n squared log n. These are better performance times. If we increase our data by 100, log of 100 is, about 7, log base 2. If we increased our data by 100 and we had an order log n algorithm, the total time required would only increase by 7x. If we increased our data by 1,000,000, the time would increase by 20. That's the log of 1,000,000. So this is a really nice performance factor. And we'll work with a lot of algorithms that are order log n, or n log n. And that's a good place to be. So a lot of what we're going to do this quarter is look at different algorithms, and as we develop different algorithms, we'll be thinking about how complex they are in time versus the complexity of the data. So we'll readdress this multiple times, but I want to use this to motivate our first data structure that we're going to dig into full force on Thursday, and this is something called a linked list. And this is also going to be the subject of your first programming assignment, which I'll post later on tonight. And the idea of a linked list is to do the things we do with arrays, but to do them with better order of complexity. So let's take a few minutes and just look at some array operations. So let's suppose we have a data array. And I'm not going to say how many things are in there, but it's an array of integers, right? And let's suppose that it's storing the following numbers: 4, 12, 7, 6, 8, 3, 19, and 2. And remember, with arrays in C, we don't know what their length is unless we record it somewhere. So I'm going to store a length integer. I'm going to set it equal to 8. To say we've got 1, 2, 3, 4, 5, 6, 7, 8 pieces of data in here. And let's suppose I have a search function, which I pass the data array, the length of the array, and the number I'm searching for. And this should return, either a 1 saying, hey, I found that number n, or 0, I did not find that number n. So how do we search this array for the number n? What's the basic algorithm? This is not a trick question.
Should just be basically start with the first element,
Yep.
see if it matches, right? If it doesn't, move on to the next one.
Yep, that's really all you can do. Unless you know this is sorted and you can play high-low or something, really all you can do is check data bracket 0, data bracket 1, data bracket 2, data bracket 3. Keep going until you get to data bracket 7. And if you still haven't found it, you can say, hey, that number's not in the array. But if I'm looking for, the number 3, and I check this one, and I check this one, hey, there's the number, I can say, yeah, it's in the array. Right? So really all you can do is just check every single element. And worst case, right, your number is either the last thing in the array or it's not in the array at all. So if I have, 8 pieces of data, it's going to take me, worst case, 8 operations, 8 times through my loop to complete my search. If I have 16 pieces of data, it's going to take me 16 iterations. If I have 160 pieces of data, it's going to take 160 iterations.
Would you factor in how much you have in a for loop to this? Like, let's say I have, 5, 10 statements versus 20, 30 statements per iteration.
What does that mean?
So if we're thinking about how many computations it's going to have to do per loop, and we're aiming to do as few of those as possible, when we're working with this orders of magnitude, orders of complexity here, will we have to factor in how big the for loop is and how
Ah.
extensive the operations are?
So this is one of the beauties of looking at the changes, right? So if it took 8 operations for 8 pieces of data, right, we're seeing that, you know, this is linear. If we do twice as much work in our for loops, right, this might be a 16, a 32, and a 320, it's still going to be linear, right? This is still going to come out to be order n, no matter how many steps we're doing inside that for loop. The thing that makes it order n is not that this matches this. It's that doubling this doubles that. So if this took 80 steps and this took 160 and this took 1600, it's still order n. When we doubled the number of data, we doubled the number of steps that had to be performed. That's what makes it order n. So that affects the total time, but it doesn't affect the order of complexity. All right, so that's a setup for what we're going to do on Thursday. We can search an array in order n. And order n is not horrible, but it's not really great either. When we look at inserting and removing from an array, we're going to see order n also, but we're going to think about how can we improve this order of complexity. And there's limits to what we can do with an array, but we're going to move from an array to something called a linked list, and that's going to improve these orders of complexity. So we'll start from there on Thursday. We'll dig into linked lists and see what they look like, and then we'll start talking about how to implement them, and that'll be programming assignment 1. All right, we're a few minutes over time. Sorry about that. Have a great afternoon, and I will see you next time.
Thanks. See you.